And now we can turn it over, I believe the chair of the next session is Claire Zurkowski, and for the session on crystallography at extremes.
Thank you, Quentin. We have 5 talks in this session, and our first presentation will be given by Leonid Dubrovinsky from the University of Bayreuth on the quantitative mineral physics and geochemistry of deep earth and planetary interiors.
Good time of the day to everybody. First of all, I would like to congratulate organizers with setting up so nice and interesting workshop. I really enjoy the program, and not only because I have been invited. I am going to talk about today about the quantitative high pressure mineral physics. I will not define what I understood under qualitative or quantitative. As we saying in Russian, it's much better once to see than 7 times to hear. So I hope when the examples which I will provide today will clearly outline what I'm considered as a quantitative or qualitative science in the field of high pressure mineral physics and the experimental geochemistry. But I would like to start with sharing with you one interesting observation. Preparing for several talks over the last months, I realized that what we are doing in the labs become the subject of the hot public, not to say the political debate. With less than a month for election in the Germany, we can see that all politicians from left to right, from the black to red to green parties, are explaining us how we should cool the Earth 1 degree down. I particularly doesn't feel that I heat the Earth too much. Maybe if politicians will become a little bit less hot, it will help. But I'm also not sure that we need to worry so heavily about the temperature of on the Earth's surface, especially if I would look at the paleo record of a temperature. It was much higher, it was much lower, it changes rapidly. And what was, from my perspective, would be really important is to understand what is going on, what is related for, and what is a perspective for changes in the Earth and our planet itself. And if you need any proof that something really happened, with a great link to the previous talk by Professor Buffett, these are variation of a position of a magnetic pole, North Pole, over the period of observation was less 200 years, not a billion years, just 200 years. The first point at 1832 have been put by the great Gauss, and we see that over this time it moved thousands of kilometers north. Certainly, this is not a responsibility of our civilization or even politicians to move this pole so much and so fast. We reasonably relate this phenomena to the process within the Earth. And our goal is, as I'm concerned, to understand what is actually going on our planet. So let me give you some examples how we can approach this question. Let us start from the long time ago, about 4 billion years ago. There are no oxygen in the atmosphere. There are no oxygen-producing organisms on the Earth's surface. There are also anoxygenic photosynthesis of primitive bacteria in ocean. And what we are doing, we're oxidizing the iron using the light and using carbon dioxide and producing a lot of iron oxide or iron oxyhydroxide. Current estimates of the speed of production of iron oxyhydroxide in those times is such that each 5 million years amount of oxygen stored in the AFOH would be the same like in the current Earth's atmosphere. And this process going not to 5 million years, it's going over a billion years. So there was a lot of accumulation of iron oxyhydroxide on the floor of primitive ocean. When plate tectonics starts, this plate tectonics drive all these sediments deep into the mantle. What happened? We know what happened with the AFOH if we will heat it at ambient conditions on the air. It's decomposed, forming the Fe2O3 and water. In fact, something similar qualitatively was found occur when we study the high pressure behavior of hematite, the mineral which has the same composition, AFOOH. So, but it was not so easy from the recovered samples from multi-angle experiments really understand what are mixture of phases observed even at relatively low pressure and relatively low temperature. Here is another example of very interesting publications which use also, I would say, qualitative approach. The analysis of the diffraction pattern, powder diffraction pattern, resulted in the assignment of some phases. Some of them are starting AFOOH phase, and some new phase which was interpreted based on this nice table as a perite type AFOOH. Or Fe2OH if you wish, and we will come back to this phase in a few slides. But what is even more interesting, that not only qualitative assignment of this data led us to the conclusion that the phase or iron oxyhydroxide is stable up to, let's say, 100 GPa and temperatures around 2000 K. But they also compare this with slab geotherm. And if you look carefully, you see that this slab geotherm assume that at the depth of around 2,500 kilometers, pressure around 120 GPa, the temperature hardly reach 1500 K. I would say that this is really a qualitative approach, and I can reproduce it. If you will take, like the authors did, the geotherm calculated up to 250 kilometers, and when linearly extrapolated it to the 2,500 kilometers, you really get these temperatures. I don't think this approach is really correct. We need first estimate which temperature and pressure we should achieve in our experiments to model the process. And we used the, I would say, semi-quantitative approach. We considered the slab one-dimensional, very simple, with a thickness 100 kilometers. When we looked on the speed with which the slab going deep into the mantle. In fact, we are interested only in the vertical component of the speed. Obviously, as faster slab is sinking, as less temperature would be in the center of the slab over its penetration into the Earth's depth. But what we know as a very nice constraint from the current geodynamic observation, geophysical observations, that there are no slabs on the Earth which are sinking faster than 1 centimeter per year. Let's consider two options: 1 centimeters and 2 centimeters, cold and fast and super fast slab, if you wish. And when we see that estimates of a temperature and depth of around 2000 kilometers are off in the previous consideration, previous publications, previous reports, around 1000 degrees. So you will use in our discussion further the data which we obtained or which we looked for these two model slabs. Now, here are a couple of diffraction pattern, powder diffraction pattern collected at IDD 13 at APS. And you can clearly see that patterns are nice, but believe me, the interpretation of this pattern just based on the observed reflections would be impossible if you don't know the phases and if you do not know the composition. So what we did, how we approached the problem, we used the single crystal diffraction in the diamond anvil cell. We looked at this thorium eye. I will not describe how we are doing this. First of all, most of you know what and how we are doing. Second, it's perfectly described in the many different publications. Third, if you really want to learn this, you can just come to the IDD 13. And I believe that Stella will teach you in the next couple of hours at least to the extent that you will be able to analyze some relatively simple cases by your own. This technique is already, I would consider it as established. We are using it, and this technique is spread over the community, even for samples which have been laser heated. Now, what we have seen. First of all, we found that if the temperatures are not really high, let's say on the level or below the super cold geotherm, we observed the known Fe2O3 phase. If you go much higher in the temperature, somewhere above the cold 1 centimeter per year sinking slab geotherm, we start to observe the high pressure Fe3O4 phase. But we also see the formation of mixed valence iron oxide, known like Fe5O7, or some new one like Fe7O10 or Fe6.3 or 9. In fact, this interesting phase deserve a special consideration, probably whole lecture for half an hour. I do not have this time, so I just couple of words. This phase was reported or observed or found in the experiments of a different group over the last, let's say, 1 or 2 years. In these publications were different interpretation of this phase. Some people say that it is over-oxidized, not hydrogen, but excess of oxygen. Some say that it is a hydrogen-bearing phase, and in these channels of the structure sitting not only oxygen, but somewhere the hydrogen. Well, qualitatively, this is correct. Quantitatively, when we look into this structure, we see that we need the fully occupied this channel by hydrogen, by oxygen, in order to satisfy the observation intensity, if you wish. We measure it from this phase. And if it would be fully occupied by oxygen, the distance oxygen would be on the order 1.3 angstrom. It is a crystallochemically impossible. It's not a plausible solution. In fact, what we see, or what we conclusion to which we came based on these experiments, and in fact on experiments in the dry system, so that channels are partially occupied, about 1/3 each position, by iron atoms. And what we actually dealing with is a structure which are similar to hollandite, very well known pseudo-hexagonal hollandite-like structure, where we also know that there are partially occupied cation position in the channel. Okay, so as soon as we have a structure, as soon as we have a chemical composition determined from the single crystal diffraction, we can determine the densities, and we can look how these densities fall along the different compositions of iron oxide or hydroxide. And as you can see, in all studied pressure from 50 to over 80 GPa, our data show that if there is some amount of hydrogen in this phase, it's a highly or very small. It is a highly unlikely. Okay, so summarizing our observation on the this system on behavior of Fe or H. We see that eventually under pressure it's decomposed with producing of oxygen and water. And when we can come back to our model, to our consideration, where layers of amount or sediments of FeOH reaching a certain depth, let's say around 1,800 kilometers, 1,000 kilometers, should start to decompose, producing the fluids. These fluids will, if you wish, not the fluids, oxygen and water rich materials, which will have a low density, and we expect it to travel up onto Earth's surface. And when it travel into Earth's surface, around 2.5 billion years ago, it may contribute or even maybe become one of the important source of oxygen in the atmosphere. It's allow us in this semi-quantitative model to explain the appearance of early whiffs of oxygen in atmosphere. It's allow us understand how the formation of large igneous provinces at time of great oxidation event coincide or be one of the source of oxygenation of the atmosphere. And it also telling us that the anoxious bacteria or organisms which live on the Earth from the around 3.8, 2.5 billion years ago was not just disappear. They were not be able to adapt to the changes in the Earth's atmosphere. So they have been replaced by the oxygenating organism. So I promised that we will talk a bit about the pyrite type structure. Yes, we observe it for both for FeO2H and FeO2. This is example of such a phase at 68 GPa. If you look carefully for oxygen distance, we will find that they are on the order of 2.14 angstrom. If you compare now with really pyrite type structures MgO2, we see that in the O2 the distance OO distance is on the order of 1.5 angstrom. Of course, we cannot expect that the compression of O2 bonds will lead to the elongation. So, in fact, we are dealing not with a pyrite type, which was assigned qualitatively, but we are rather dealing with a high pressure palladium fluoride type structure, which we can determine from a single crystal diffraction. We still don't know if we are dealing with the iron 2+, iron 3+, iron 4+. And what is oxidation state of oxygen. Theory suggests us that not only MgO and FeO2 are significantly different, we're telling us that there are no real bonding between the oxygen atoms. Mersbauer spectroscopy show us that there is this green component which we attribute to AfO2, and it means that iron is the 3+ oxidation state. The same telling us the measurements of compressibility of this material. It's on the order of 300 GPa, and it means that this is certainly not Fe2+ compound. We can compare from single crystal diffraction data results of measurements of AfO6 octahedral volume for different compounds studied by us, but also by other groups, and we can see that these large stars, that the volume of the octahedra is smaller than any other known so far compounds with octahedral coordinated iron. It means that we most probably dealing with the oxygen with oxidation state 1.5 minus. This has, from our opinion, very significant implication not only for interpretation of the nature of AfO2, but also for interpretation of the behavior of a silicate perovskite. These are relatively old slides, but only now we can start to discuss that the changes in the amount of iron upper perovskite or post-perovskite composition may be related to the changes in the oxidation state, not only iron, but also oxygen. In fact, the investigation of recovered samples give us clear proof that there is a decomposition reaction, and you see here the piece of Fe3O4. Now, if you look on the series of synchrotron Mersbauer spectra collected on the material with different composition and different ratio of iron silicon, I do not have time to go in any details, but what I wanted to say, that we not only clearly observe the incorporation of a small amount of iron 3+ into the octahedral position, but we also see that in the post-perovskite phase, we see the kind of sign of magnetism, and we also see, if we will analyze it carefully, that it's probably not a fully occupied oxygen position. It brings us to the idea that somewhere in the significant depths, where oxygen, not only iron, but oxygen change its valence states, and may be another major geochemical elements with a variable oxidation state. Okay, I probably have a couple of more minutes. So carbon, it's another not so probably abundant as oxygen iron, but still very important component of subducted slabs and the mantle, which may change the oxidation state. Few years ago, we demonstrated on basis of studies of, on the example of studies of iron carbonate at high pressure, that there are series of orthocarbonates of iron. It's always question, is this can be produced only from the starting from already oxidized carbon, or it may be produced from the diamond. Well, in one of our series of our experiments, we loaded iron and oxygen, and what we have seen as a product of a reaction, well, the same orthocarbonates which we observed originally only as a product of a decomposition of FeCl3. It means that in fact, if the oxygen fugazi is significantly high at high pressure, we can easily oxidize carbon, and or we can have oxidized carbon. I do not know if it's oxidized by oxygen or it's oxidized or it's involved changes in the oxidation state or activity of iron. One more quantitative observation. At 45 GPa, we found a new phase, which has a composition Fe3CO7. You can immediately calculate. You can immediately calculate that the oxidation state of iron, even if we will take that it is 3+, it's not. It doesn't allow oxygen to be 2-. So we have a clear confirmation that it is really iron's just a 3+. It doesn't change its oxidation state, but where oxygen has a lower charge or oxidation state. Okay, so what I want to say here, that looking at all evidence which are presented in slides which I showed to you, we can make a rather complex picture of the behavior of Earth's chemistry. If you look now on this pretty busy diagram, you can notice that the formation of the large igneous provinces are somehow really coincide or very close to the event of the major extinction or known on the Earth. It means that, at least as I can read such type of data and information, that Mother Nature telling us, I gave you the brain, not in order you put it somewhere in the sand, but in order to give you opportunity to adopt, to change what you are doing and how you are doing, in order to cope with what changes can happen on the planet. It doesn't mean that we should destroy our planet, but we should understand that somehow we are still not in the power to control everything or all processes within the planetary body. Now, in order to be served for the community, in order to move in this direction, we need a proper tool. As Peter yesterday told you, we are working hard on the making the instruments for nano-diffraction studies and high and very high pressure. This is example of a nano-diffractometer, and I'm happy to report that with this machine, even in the, let us see, not advanced PO2 beamline in terms of intensity, I can say, advanced beamline like PO2, we can already collect the data and solve the structures at pressure over 200 GPa. We are working hard on the development in situ high pressure, high temperature crystallography. Some development in this direction already exists, but the setup is not so, I would say, user-friendly, and we are putting a lot of effort to make it possible to work with DARTs, Diamond Anders Round Table. You can see the example of a setup which we now playing in Bayreuth. And I believe that all this development will help or can be used not only in Germany, but also and fortunately at a new APS facility, and allow to perform for community where real quantitative studies in field of a high pressure mineral physics. Thank you very much for your attention.
Thank you, Leonid. Looks like we have one question and time for a quick question from Sergey Labanov.
Hi, Leonid.
Hi.
Thank you for your talk. I understood it mostly. I have a question on how you modeled the temperatures inside slabs as a function of their speed. Could you please go a little bit into details how exactly that was modeled, and what do you need from those guys for measuring thermal conductivities? And
no, we did not. Okay, let's put it like this. We did not use any advanced results on the thermal conductivity of silicates, function of pressure and temperature and all this. It was as I told you, it's not a quantitative. This is a semi-quantitative science. We use the certain numbers and see that they are not so many. Of course, I would not be able to do it in the 20 seconds which we have now, but it is published. It's published recently in European Journal of Inorganic Chemistry. First author is Koimets, and when we will be done, I will just send you the reprint of a paper. So you will be able to read it. If you will have a question, you're absolutely welcome.
Thank you.
Right. Thank you, Leonid.